Welcome to our third set of fluid mechanics practice questions. In this video, we will dive into fluid dynamics. Ensure you are referencing the FE handbook while answering these questions. As a supplement to this course, check out the full-length practice exams and other topic-specific practice questions that can be accessed through the link in the description. Now, let's get started with some fluid mechanics practice questions. Practice question 1. Water flows steadily through a horizontal pipe that narrows from a diameter of 0.2 meters at section 1 to 0.1 meters at section 2. If the velocity of the water at section 1 is 1.5 meters per second, what is the velocity at section 2? Assume the fluid is incompressible. We begin by applying the principle of conservation of mass using the continuity equation. For an incompressible fluid flowing steadily through a pipe, the volumetric flow rate must remain constant throughout the system. That means the product of the cross-sectional area and velocity at section 1 must equal the product of the cross-sectional area and velocity at section 2. We compute the cross-sectional areas of both sections based on the given diameters. The area of a circular pipe is found using the formula pi over 4 times the diameter squared. Once we know A1 and A2, we solve for the unknown velocity at section 2 by rearranging the continuity equation to isolate velocity. Plugging in the known values gives us V2 equal to approximately 6 meters per second. Thus, the correct answer is option D. Practice question 2. Water flows steadily through a pipe that rises 4 meters in elevation from section 1 to section 2. The pressure at section 1 is 250 kilopascals, and the velocity is 3 meters per second. At section 2, the velocity increases to 5 meters per second. Assume the pipe is flowing water with a specific weight of 9,810. What is the pressure at section 2? To find the pressure at section 2, we apply Bernoulli's equation in terms of specific weight. This form of the equation includes 3 terms, pressure head, velocity head, and elevation head, and assumes the flow is steady and incompressible with negligible losses. We begin by setting up the equation using the given values at section 1 and section 2. This results in the following simplified equation where P2 is the only unknown. Now, we can solve for P2 and simplify. This results in a pressure of approximately 202,633.84 pascals. Matching this to the closest answer choice leads us to answer choice B. It is important to note that not all final answer values are intended to match exactly with the answer options provided when taking the actual FE exam. Sometimes you must choose the closest answer option. Practice question 3. A chemical processing plant uses 2 different fluids to transport materials through pipes of the same diameter and length. Fluid A has a lower dynamic viscosity than fluid B, but both fluids are pumped through their respective pipes at the same average velocity. If all other conditions are equal, which of the following statements best describes the flow behavior in each pipe based on the Reynolds number? We begin by recalling the definition of the Reynolds number. Reynolds number is a dimensionless quantity that characterizes the type of flow in a pipe, whether it is laminar, transitional, or turbulent. It is directly proportional to the velocity, diameter, and density, and inversely proportional to the viscosity. Next, we analyze the fluid properties provided in the problem. The question tells us that fluid A has a lower dynamic viscosity than fluid B. Both fluids are flowing through pipes of the same diameter at the same average velocity, and we can assume the same fluid density for both since nothing to the contrary is mentioned. Given these conditions, the only varying factor in the Reynolds number expression is the viscosity. Because fluid A has a lower viscosity and all other factors are equal, fluid A must have a higher Reynolds number than fluid B. We then consider how the Reynolds number relates to flow regimes. From the reference ranges given in fluid mechanics, a Reynolds number below 2,100 indicates laminar flow, above 10,000 indicates turbulent flow, and values in between suggest transitional flow. Since fluid A has a higher Reynolds number due to its lower viscosity, it is more likely to enter or approach the turbulent flow regime compared to fluid B. Therefore, the most accurate interpretation is that fluid A will have a higher Reynolds number and is therefore more likely to become turbulent. This matches answer option C. Practice question 4. A firefighting hose delivers water through a straight, horizontal steel pipe that is 60 meters long and 0.12 meters in diameter. The average velocity of water in the pipe is 3 meters per second. The Darcy friction factor for the flow conditions is 0.028. Using standard gravitational acceleration 9.81 meters per second squared, what is the head loss due to friction in the pipe? We begin by recognizing that this is a classic application of the Darcy-Weisbach equation. This equation relates head loss to pipe length, pipe diameter, flow velocity, gravitational acceleration, and a friction factor. We first calculate the length-to-diameter ratio, which is 60 divided by 0.12. This gives us 500. Next, we compute the velocity squared term divided by twice the gravitational acceleration. This gives us approximately 0.4587. Now we multiply all the components, the friction factor, the length-to-diameter ratio, and the velocity term. This results in a head loss of approximately 6.42 meters. Therefore, the correct answer is option D. Practice question 5. A concrete-lined trapezoidal irrigation canal is designed to carry water down a gently sloped farm field. The canal has a cross-sectional area of 2.4 meters squared and a wetted perimeter of 3.2 meters. The channel slope is 0.0008 and the roughness coefficient for concrete is 0.015. What is the expected flow rate of water through the canal in cubic meters per second? Use K equals 1 for SI units. The given values include the cross-sectional area, wetted perimeter, channel slope, roughness coefficient, and the SI coefficient for Manning's formula. Next, we calculate the hydraulic radius, which is defined as the area divided by the wetted perimeter. This gives us a hydraulic radius of 0.75 meters. Now that we have all the values needed, we plug them into the Manning's equation. Computing this gives a final flow rate of approximately 3.48 cubic meters per second. So, the correct answer is choice B. Practice question 6. A pipeline carries a compressible fluid horizontally through a segment where the fluid experiences a rapid deceleration due to valve closure. If the elevation at both ends of the segment is the same and the fluid density remains nearly constant, which of the following best describes the resulting pressure change from location 1 to location 2? First, we recognize that the flow is unsteady because of a rapid deceleration. That temporal change means local acceleration exists. Since the fluid is moving horizontally, there's no change in elevation, so we can ignore gravitational effects in the vertical direction. The problem also tells us the density of the fluid remains nearly constant, which allows us to simplify the relationship between pressure and acceleration. Now, to understand what happens to pressure, we recall a simplified version of Euler's equation. This tells us that the change in pressure between 2 points is directly related to the local acceleration acting along the length of the pipe. In this case, the flow is decelerating, meaning the acceleration is negative in the direction of the flow. When we apply this concept mathematically, we see that the negative acceleration causes the pressure difference to be positive. That means the pressure at the downstream location, location 2, must be greater than at the upstream location, location 1. This makes physical sense too. When fluid slows down rapidly, it compresses slightly if it's compressible, which creates a buildup of pressure behind the point of deceleration, in this case, just upstream of the valve. So, in order to oppose the deceleration and maintain momentum conservation, the pressure at location 2 must be higher. Thus, the correct interpretation is that the pressure increases in the direction opposite to the negative acceleration and therefore, the pressure at location 2 is greater than at location 1. This means answer choice C is correct. Practice question 7. Water flows through a pipeline that splits into 2 parallel branches, Pipe A and Pipe B, before rejoining. Pipe A has a diameter of 0.10 meters and length of 50 meters, while pipe B has a diameter of 0.15 meters and length of 75 meters. The friction factor for both pipes is the same, 0.02. The total volumetric flow rate through the system is 0.020 cubic meters per second. Assuming the head loss is equal in both pipes, what is the flow rate through pipe A? To determine the flow rate through pipe A in this parallel piping system, we begin by using a key assumption provided in the problem. The head loss is the same in both pipes. This is typical for parallel flow systems, and it allows us to equate the expressions for head loss in each pipe. By setting the two head loss expressions equal to one another and simplifying with the provided dimensions, we find that the velocities in both pipes must be the same. This simplifies the rest of the analysis because we no longer need to treat the velocities separately for each pipe. With this established, we can now use the principle of conservation of mass. The total flow rate through the system must equal the sum of the flow rates in both branches. Since the velocities are equal, the total flow is the common velocity multiplied by the sum of the cross-sectional areas of pipe A and pipe B. We calculate those areas using the standard formula for the area of a circle and sum them to get the total area for flow. Next, we solve for the common velocity by dividing the total flow rate by the total cross-sectional area. With the velocity known, we multiply it by the area of pipe A alone to find its individual flow rate. The final result, after rounding appropriately, shows that the flow rate through pipe A is approximately 0.006 cubic meters per second. This corresponds to answer choice B. That concludes our practice questions for this unit in fluid mechanics. In the next lecture, we will continue with fluid mechanics and cover part 2 of fluid dynamics. Again, if you want more example questions or complete FE practice tests, visit the link in the description or on screen. Thanks for watching.